Okay, hello? That's working, yep. I think we're going to get started because we don't see any new people filing in anymore, so I think we're at a steady state here. So welcome to the 2022 lecture series for the Arntzen Grand Challenges. This is, as you know, an annual event for us at Biodesign, and we're really excited for this year. I'm going to take a moment here and just remind you a little bit about who we are. So we're the Biodesign Institute. We're a research institute here at ASU. We like to say that we do three things here. We illuminate threats, we mobilize teams, and we shepherd solutions. And what that really refers to is our desire to tackle world problems. Our focus in the Institute is always research with the intent of solving major problems. And that requires first identifying and understanding the problem, building an interdisciplinary team to help solve it, and then making sure that you take that solution all the way into action. We don't want to just write the paper and walk away. We want to see that it actually leads to something important.
If I had to pick a point in time for why be a scientist, I was standing in the backyard of our farm sometime in the 50s, and Sputnik went over, the first satellite. And my father would point up in the dark sky and say, "That's Sputnik. That's what the Russians are doing. You need to go to college and participate in catching up with what's happening in Russia." When I came to ASU, I was given an endowed professorship funded by Florence Ely Nelson. I plowed that money into the first studies we did of vaccines produced in plants. And it was at a time when the ideas we were generating were crazy enough that it was hard to get funding from the federal government. That is, they were sort of outside the box. And having support from an endowed chair at ASU gave me the flexibility to hire some people, students, to try some new ideas. And fortunately for us, it clicked. It really worked well. I was taking a weekend off in Thailand. It was there for some collaborative research. Went to the river market where the boats come in, and I saw a woman with her baby buy a banana, peeled the banana, and gave it to the child. And I thought to myself, what can I do to re-engineer a plant so it has direct medical purpose? In talking with one of the professors at Baylor, we pulled together the idea, let's produce vaccines in plants. And we jointly did the very first project on a hepatitis B vaccine. And when we tested these plants, they produced an abundant amount of the structural component that's used today in the hepatitis B vaccine. Few scientists in their career actually see something that started on the bench and goes on to have an impact that's tangible. And you can make a straight line connection between the two things. So it was in 2014, one of my colleagues in San Diego that we'd collaborated with called in the morning. I was sitting in the kitchen, and he said, "I don't know if you heard the news, but there's an Ebola outbreak." And we sent some of our ZMapp, it was this drug we jointly developed for Ebola treatment. We sent some of this to Liberia, and they've used it in some missionaries. We designed it here at Biodesign Institute, and our collaborators in San Diego and collaborators in the U.S. Army carried it forward and tested it, and it worked. That's amazing. I think everyone needs to be shocked with new ideas occasionally. Something that changes your day-to-day thought process, and all of a sudden, bam, that's really exciting. I had no idea that was happening out there. So the idea of a Grand Challenge lecture series was bring in new ideas, bring in the cutting edge of science, and create the opportunity for our students, the faculty, everybody in biodesign to interact with this with the ideas and with the people bringing them to the forefront. I'm Charlie Arntzen. Welcome to the Arntzen Grand Challenges Lecture Series.
Okay, yes, so I don't have to do as much introduction as I thought I did because that video did such a great job of it. But we're really here to honor Charlie and all the work that he's done for us at Biodesign. You know, Charlie was the first director of our institute. He's the one who really got it off the ground. And as you saw from this video, his work has been groundbreaking both in terms of discovery, but also in terms of taking that discovery towards application, one that was successful and one that we're all very thankful for. So it was really because of Charlie that we've set up this series. He helped underwrite this series, and as you heard, it's really about bringing exciting lecturers to speak. So first of all, I'd like to give a hand to Charlie. And then I'm going to hand off the microphone here because I want one of our esteemed faculty members, Bruce Rittman, who himself has done amazing things, is a Stockholm Water Prize winner and important researcher in the field of water sustainability, because he's a personal friend of our speaker tonight, and I think he'll do a better job introducing him. So I'll bring you up, Bruce.
Okay, thank you, Josh. Well, it's my distinct pleasure and honor to be able to introduce our speaker tonight, Dr. Jerald Schnoor. So he's the Alan S. Henry Chair of Engineering and Professor of Civil and Environmental Engineering at the University of Iowa. He's been at the University of Iowa since 1977, and I've had the great personal pleasure of being able to do a number of things with Jerry directly and with his colleagues at the University of Iowa. He's famous for his work in sustainability and phytoremediation. Charlie Arntzen will be particularly happy about phytoremediation, using plants to clean up pollution on this. And he's been working in the area of climate change since long before it became trendy. So Dr. Schnoor has a lot of accolades that are well-deserved. First of all, he is a member of the National Academy of Engineering. The American Society of Civil Engineers has honored him with a number of awards: the Huber Award, the Herring Award, and the Fries Environmental Engineering Award. He was the 2010 winner of the Clark Prize for Outstanding Achievement in Water Science and Technology for the National Water Research Institute. He's won the McCarty Founders Award from the Association of Environmental Engineering and Science Professors. But the one thing that I want to point out here, and it'll be my last thing to point out about Dr. Schnoor, is that in 1998, he was the Distinguished Lecturer for the Association of Environmental Engineering and Science Professors. And he toured all around the country giving talks. And at the time, I was at Northwestern University. He came to Northwestern University, and he gave a wonderful talk on global climate change, and it was 1998. So he's been working in this area, been a leader in sustainability and understanding and responding to climate change since certainly since the 1990s. So let's please give a warm welcome and extend our thanks to Dr. Schnoor for his wonderful presentation tonight. Jerry?
Bruce, thank you. Thank you. It's an honor and a privilege to be here today. I had a wonderful visit at ASU, as I always do, and I want to first of all thank Josh LeBert, Bruce Rittman, Laura Grosso for arranging this visit, which I'm very grateful for. And I also see some students in the crowd, and I must tell you I had a wonderful time talking to the students of the Biodesign Institute and Arizona State University, because they're really the ones who have to address some of these grand challenges that so rightly you have designed a lectureship around. So thank you very much for the chance to be here. I'm trying to talk tonight about sustainability in the face of climate change. And if sustainability somehow means keeping on doing what you've been doing, your activities, for the foreseeable future for this generation and for future generations, when everything is changing about us, and I guess that's the thesis tonight, we have to act faster and faster and faster just to try to maintain the status quo. And I told the students today at lunch that really my version of sustainability is something a little bit even more. I don't want to just keep going for the foreseeable future. I want to do it better. And if we can address this climate change problem, we can inherit a society that is much better. That's sort of the thesis for today. I have to tell you how pleased and privileged and honored I am to be able to give in the Distinguished Lecture Series for Charlie Arntzen, because as it says up here, I know that he's the founding director of the Biodesign Institute. He's a member of the National Academy of Sciences in the U.S., in India, by the way, too. I don't think that was mentioned. He's a U.S. Academy of Inventors AAAS fellow, but best of all, and most of all for me, he's a plant guy. He's a plant guy first and foremost, and I fancy myself interested in plants as well. This is the big blue marble that we're talking about, and if you think about, I looked it up, we're now, at the end of this year, close to 8 billion people on Earth, if you can imagine. And I also looked it up, and we're close to, if you sum up all the country's gross national products into a gross world product, we're pushing $94 trillion a year now. Whenever you have that much activity, 8 billion people, $94 trillion in manufacturing and technology, you're going to affect the smallest compartment we have on this big blue marble, and that's, I don't even know if you can see it, it's the thin veneer on the blue marble that we see here called an atmosphere. And it's no more than 50 kilometers thick, and it's actually a very small compartment. And when you have that much going on, it's easy to change the steady state. We've enjoyed, in the Holocene period, the last 11,000 years, the Earth has been at a relative steady state, which has enabled us to do agriculture, enabled us to build cities, but now that steady state is abruptly changing. And the talk tonight is about how is it changing and what can we do about it. It's not only the atmosphere, as it turns out. If you would have told me as a young chemical engineering student that we could change the entire oceans in my lifetime, I would have said, you're crazy. There's no way that we can possibly affect that kind of a thermal mass in just one human's lifetime. But in fact we have. So you may know also that this year a new report has come out, the 6th report in a series from the Intergovernmental Panel on Climate Change, the United Nations, and Secretary General Guterres called it a code red for humanity. The time is up to really start to do something. We have to act now if we want sustainability. And the report reports here that it's unequivocal that humans have influenced the atmosphere, ocean, and land. We need to reduce our greenhouse gas emissions by 45%, or roughly half, by 2030, and to be completely out of the fossil fuel age, net zero in 2050. In fact, the carbon dioxide concentrations have never been this high before in the last 2 million years. So we are really at a precipice that hasn't been seen even in geologic time. CO2 is accumulating in the atmosphere. I think you know the story. The red arrows going up are bigger, unfortunately, than the black arrows going down. The red arrows have to do with burning of coal, oil, and natural gas, some of which the coal, since the Carboniferous age, took 340 million years to form in the Earth's crust, and we're digging it up and burning it in a couple hundred years, just the blink of an eye in geologic time. Of course, when you take something that took 340 million years to form and you burn it up in a couple hundred years, of course you're going to change that smallest compartment on Earth, the atmosphere, the thin veneer held by gravity onto the skin of the Earth, and we have. And what it amounts to is that it's not that we're running out of coal, oil, and natural gas. I'm here to tell you that we have enough to last many, many decades, if not centuries, but we can't even burn that which is already in proven reserve. What we're running out of is a place to put the exhaust from all of those fossil fuels, and that's the atmosphere. And the red arrows being bigger than the black arrows going down mean that roughly we have 16 billion metric tons per year of carbon dioxide accumulating in the atmosphere. It's a trace gas, but it wouldn't matter too much, but it's a radiatively important trace gas. It changes the energy balance, much like wrapping a blanket around the atmosphere and keeping the heat in. Unfortunately, ever since the Industrial Revolution in the late 1700s, our emissions have just gone up and up and up with that growing population to 8 billion people. There have been a few blips. You can see at the beginning of the pandemic in 2020, it went down 6 or 7%, but it went right back up after the pandemic in the last year. And what we need to do is have that red line, we need it to come down about like I've shown on the red line. And we haven't even turned the corner yet. We haven't even hit our maximum emissions, peak emissions, in order to bring it down by half in the next 8 years. When you put up that much emissions, it means that the carbon dioxide concentration in the atmosphere is going to grow, and as you know, it has. We're currently, if you average north and south, it's about 418 parts per million right now. It started off at 280 parts per million in the Industrial Revolution, and that's about a 50% increase. I would submit, I told somebody today, if you went to the doctor and this was your blood gas profile over time, I think you should be concerned. And indeed, for planet Earth, yeah, we're concerned. About 65% of the radiative effect is due to carbon dioxide alone, and that's the one we'll talk most about tonight, but there's others we can engage in as well. When you have a radiatively important trace gas like carbon dioxide, which is keeping the heat in the atmosphere, it means that eventually you're going to raise temperatures. And the y-axis here is just the anomaly, what we call the temperature difference since long ago, going up to 2020 and beyond. And basically what you see is that the 1980s were warmer than other decades. That's where the signal began to emerge from the noise, the interannual variability. In the 90s were warmer than that, in the 2000s warmer than that, and so on, and such that in the last 8 years consecutively have been the 8 warmest years on instrumental record on planet Earth. So the trend is clear. The signals emerge from the noise. There's no doubt about it. We've warmed about 2 degrees Fahrenheit so far, a little more than 2 degrees Fahrenheit so far. We're not just breaking temperature records, we are shattering them. This last March, we had 40 degrees above normal temperatures in the Antarctic, and at the same time in the Arctic, 30 degrees Fahrenheit warmer temperatures in the Arctic. Both poles, 30 or 40 degrees warmer than normal, if you can imagine. We are shattering records, not just breaking them. There's, depending on the year, 2 or 3 more high temperature records set every single year all around the country on a given day than low temperature records. You know the statistics when that's happening. You know that indeed you're really warming up. When you warm up, if you have a little bit of soil moisture, it goes out faster, meaning that droughts tend to be more frequent and also elongated, longer periods of time. At the current time, we have something like, 2/3 of the United States in some kind of drought, including Arizona, of course, and maybe if you can see right in the center of the country, I can't show everybody at the same time, in the center of the country, even Iowa, we're in a drought right now also. So this is going to be a more and more frequent pattern, even though the hydrologic flywheel is spinning faster and faster, meaning the oceans are warmer, more evaporation, more moisture in the air, humidity is going up tremendously, and more clouds means more rainfall. So overall, more rainfall, but it's punctuated by drought. That's the extremes that we're experiencing. Just in recent decades, major rivers no longer flow to the sea. You know better than anybody the Colorado River on the right here. My daughter was there recently and took that picture of Lake Mead for us. And I was recently in the Yellow River in China, but it's not just the Yellow River and the Colorado River. We're talking about major rivers all over the world. The Indus, the Amu Darya, the Teesta, the Murray River in Australia. They used to make it to the sea regularly every year, and they no longer do. It's not, as you know, it's not just climate change. I don't mean to intimate that. It's climate change, the population that we talked about earlier, and the need for more and more food to feed more and more people, with irrigation being 70% of all water consumption. So it's the increased irrigation, the increased people, the withdrawals, and also, climate change, changing the patterns of the weather. I show you this one from January of this year, the Big Sur wildfire, because my son lives very near here in Monterey, California, in the hills behind Monterey and Carmel. And this one affected him. He's had to evacuate his house twice so far. Cal Fire, those guys ought to all have medals. I mean, they work so hard against unbelievable conditions. They've saved his house twice. But that's just in the last couple of years. This one along in Big Sur, that's Pacific Coast Highway right there. You may recognize in Highway number 1. When you have wildfires and warmth and heat, you also have melt. And the ice is melting. It's adding to sea level rise. Roughly half of sea level rise that we're experiencing is due to meltwater coming off of continental glaciers like shown here in Greenland. And about half of it is due to the thermal expansion of the oceans as the waters begin to warm. This one I put up in memory of Conrad Steffen. Connie Steffen died. He actually started the Swiss camp trying to measure the flow of water in the summertime mostly on Greenland and getting our first good estimates of it. Now we do it by gravimetric satellite. That's another story. But he fell down into the Moulin, lost his life. Connie Steffen he had asked me to go there, and I told him I thought I was too old. And I think I'm glad, actually, that I said that, because it's dangerous, as you can imagine. It's not only in Greenland, it's also in Antarctica. We've known for a long time, in fact, the Thwaites ice shelf in western Antarctica has often been called the Doomsday Glacier, because if it's partly balanced, if I had a chair I could show you, it's partly balanced on the continent, on Antarctica, and partly hanging off into the sea. And if it falls into the sea, then the other glaciers come faster, continuing to add to sea level rise. It would be about 3 meters of sea level rise, and we call that abrupt climate change. And the previous reports that I mentioned from the IPCC didn't even talk about that, because as humans, we don't really know how to deal with the risk assessment. Tonight at dinner, we were talking about risk assessments of what kind of risk assessment, what conclusion do you have when the consequences are huge, let's say infinite, but the probability is small, let's say 0. This is a test, guys. Get out your particular. What do you get when you multiply 0 times infinity? It's undefined, right? That's what we're up against in trying to deal with these threats. The one on the right, the Denman, that is something new this year. We never thought the East Antarctic ice sheets were even unstable, but this one is unstable. If it fell in, it'd be 1.5 meters threat. Just now, the reports are beginning to try to deal with the probabilities and the consequences of so-called abrupt climate change. Never before, really. You know, if you want to know how hot is it, and that's a good question, you should go to the oceans, that largest thermal mass that we talked about on the very first slide. You should go to the oceans because that's where the extra heat, it's a top-down warming, but that's where the extra heat has gone from the atmosphere into the oceans. That's where you can measure it. It's really the only place you can measure it. We sent up a whole bunch of satellites. Arizona State was involved in it. The series of satellites, and we can't really measure the balance, the energy balance from satellites in the atmosphere. Very difficult because of the cloud cover, the extreme variability through the seasons and location. But the oceans are more well-behaved. And it's only since 2005 that we have begun to know how much heat is it that we're adding. And we have a pretty good idea now since 2005 due to this Argo program, which the United States is a part of that one. It's a big international program. There's about 4,000 SONs or floats going right now. You can, on your laptop, you can find out where they're floating at any given time in real time. There's a static snapshot of it in the bottom here. It's just a probe, a simple one, shown on the right-hand side, which comes up and on about a 7 or 10-day cycle, regenerates from the sun, recharges from solar, and then goes down through a programmed dive to 2,000 meters, or now we have some that go deeper, to 2,000, measuring very precisely the temperature, the pressure, the salinity, very precisely, 4,000 SONs continuously floating. So only now can we begin to understand what the heat content of the ocean is. And when it comes up, it sends its data, transmits its data to the experts. Experts like at NOAA, who measure that data, and this is the heat content. I know 10 to the 22 joules doesn't mean much to any of us, but let me tell you, it's a lot of heat. So I had my students make this calculation. The Hiroshima bomb, sadly, was about 62 trillion joules in that bomb. And what's going on now, the heat added to the ocean, is about like 7 Hiroshima bombs going off every single second, 24 hours a day, 365 days a year. That's how much heat we're adding to the ocean. It's immense. It's an immense amount of heat. To put it into some perspective, it's something like more than 20 times the heat generated from burning all the fossil fuels. You know, the heat from that. It's way bigger than that. And it's just from putting radiatively important trace gases that vibrate and rotate when back radiation is shined on them and generate heat, like the blanket wrapping the Earth. I have to mention, you know, most of these things we're talking about, ice melt, even sea level rise to some extent, temperatures, soil moisture, so forth, all of them are reversible on some time scale. It's decades and decades, but they are reversible. This one is not reversible. That is that we're also, and it's not just climate change is just one factor, but we're also losing species like crazy. At more than 100 times the natural rate of extinction. New species are being created by evolution, but much, much slower than how we're losing them. We don't even know how many we have. The best estimate using AI, a recent one that I looked up, was 8.7 million species. But we only have Linnaean, Latin genus and species name for about 1.4 million. So if we're losing 1 million in your lifetime, we don't even know which ones we're losing. We don't even have names for them. But when they're gone, they're really gone. That's completely irreversible. Forget Jurassic Park. We don't have a genealogical zoo going on unless Arizona State has started one since I checked last time. It's really gone. And you should also know it's not just climate change here. Habitat destruction is still number one, both on land and on sea. And we're losing insects, we're losing amphibians, reptiles, birds, mammals, and Yeah, Charlie, plants. We're losing plants too. Valuable genetic material. So what's our future? If it's going to be sustainable, we might be able to endure, the IPCC thinks, more warming. We're at 1.1 Celsius now, maybe or 2. Maybe we can go to 1.5 degrees Celsius and not have too much worse effects than we're talking about already. And that means we only have 11 years left at current emissions. The most recent report I saw indicated that some estimates, this is an AI estimate also, based on the policies that are going into play around the world and the pandemic and maybe a recession too, that even with all those things we're talking about, probably 11 years is the most we can expect. We'll probably, by 2030, our goal is 50% decline in emissions, but right now we're scheduled for 1% decline in emissions. We haven't even begun to turn the corner. When we do, we should have some kind of great planetary party, because ever since the Industrial Revolution, it's done nothing but emissions go up, 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 and we still haven't been able to turn that around. What I've been working on recently, I haven't even had a chance to tell Bruce about this, I've been working on the chemistry of the oceans, following one of my mentors, Werner Stumm, at the Swiss Federal Institute of Technology. He asked long ago, what is the PE of the sea? What's the oxidation reduction potential of the sea? And it struck me when I tried to answer that question that, like we said on the first slide, everything is changing. Everything is changing. There's no steady state. The ocean was never in a steady state. In fact, the ocean was never in chemical equilibrium, but it was in a steady state through the Holocene period. And now that steady state is being disrupted, and that's a big part. Why is it disrupted? Due to a massive disruption in the elemental cycles of carbon, nitrogen, and sulfur on Earth. From mining things that took millions of years to form and burning them and releasing them in just the blink of an eye. The master variables affect all chemical, physical, and biological reactions, everything. We haven't even begun to figure out what are all the effects, really. But their temperature, pH, the oxidation reduction potential, or the PE, that's the negative, that's a logarithm of the electron activity, and dissolved oxygen. They're all changing, and it's a big concern. This is a paper I wrote recently for ES&T on the land. When we burn up all of those fossil fuels, we create carbon dioxide and temperature increases in the atmosphere, which are transferred down, top down, into the oceans. And the bottom left-hand reaction is one I want to mention. That's the Haber-Bosch, they got the Nobel Prize for the Haber-Bosch reaction to make ammonia from nitrogen gas in the atmosphere. But it's really not sustainable in the sense that you take nitrogen, unreactive nitrogen from the atmosphere, and you combine it with methane, natural gas from our fossil fuels, and you end up putting out carbon dioxide and copious quantities of ammonia. Ammonia and phosphorus fertilizers that are running off of the land and beginning, I hope to show, beginning to affect, yes, even the open ocean. This is a view of, from NOAA, of we can use isotopes to figure out the signature of fossil fuels is unique. We can figure out the carbon dioxide from the fossil fuels, where it has gone. And this is just since 1989, so what is that, 33 years. In the last 33 years, the purple shows where the carbon dioxide has gone. It's gone down 3,000 meters into the open ocean, shown here. And of course, it's acidified, that 3,000 meters. Now, carbon dioxide is more soluble in cold water, so you'll notice it's a northern ocean and a southern ocean phenomena. There may even be some degassing in the tropical or equatorial oceans. This is my daughter. We went on a scuba in the Great Barrier Reef off the northern coast Antarctica. Bruce knows her and has met her as a family friend. And they're so colorful and so beautiful, but we're losing them. And the two main factors really are the acidity now and the increased temperature. You know, it's a mutualism, as you know. The animals, to make the skeleton for the coral reef, they have to form calcium carbonate from the sea. And then the algae, which make it so colorful and beautiful, they form in the polyps of the skeleton of the animal. And it even has a big effect on fisheries, as shown here. Also, there's other factors involved as well. This is the most technical slide I have in here. I told Laura I should have taken it out. But how much is the ability to make that coral, how much is it being decreased? And the answer is a lot. 0.5 or 0.6 aragonite. There's 5 main mineral forms, polymorphs of calcium carbonate. One of the most important ones for the sea is aragonite, and that's the most soluble one, and that's what the coral needs to form their skeleton. And the saturation, because of the acidity from the CO2, a weak acid, the saturation level of calcium carbonate, aragonite, has come down a lot. And just in recent years, and is now in danger of many, many coral reefs. Maybe somehow thermodynamically they'll still be able to form calcium carbonate, but I doubt it from a thermodynamic standpoint once you go under saturation. The waters have to be supersaturated in order to form the shells. The biggest surprise to me, again, in researching this is that I knew about the red dots on this. I don't know if you can see the red, but there's about 500 red dots on the coastal areas of these continents, and they're all hypoxic areas, very low in dissolved oxygen. Most fish can't live there, shrimp can't live there, and that's all over the planet. But the news story is, for tonight, that it's also the open oceans. The oceans between 200 meters and 800 meters are beginning to lose oxygen. So a problem that we thought was a coastal problem is now, because of our hubris and our tremendous power, 8 billion people and 94, we're beginning to affect the open ocean with deoxygenation. Very sobering. The main researchers think that about 15%, the blue areas are the open ocean areas. About 15% of that loss is due to the solubility in oxygen isn't as soluble in warmer waters, and the oceans are warming. And then about 85% of it is thought to be due to a decrease in mass transfer down of the oxygen due to thermal stratification, and also the increase now in nitrogen and phosphorus coming off of the land, the Haber-Bosch process. This is a view from the recent paper which I wrote, in which the CO2 is going up in the atmosphere. That causes the temperature and pH, temperature to go up, pH to go down. That in turn, with stratification, causes the dissolved oxygen. And the PE of the sea, by my calculations, is in those open areas of deoxygenation, gone from about 12.5 to 12.3. That may not sound like much, but it's a first. And it's something to be very, very concerned about. The sustainability here at Arizona State, the emphasis is really admirable to me. I feel you're very lucky to be here and have this emphasis on sustainability. And of course, it affects the food, energy, water nexus. My students tell me every country should be able to be food secure, water secure, and energy secure. Yes, every person should be able to be food secure, water secure, and energy secure. Yes, and if that's so, because of the changes, we have to go very, very fast in order to keep up. We need about 60% greater food production by 2050. It's estimated when we'll have close to 10 billion people on Earth. We have to do it with regenerative agriculture. We have to do agriculture in a different way. I already mentioned about Haber-Bosch process. That means I'm interested in microbial fertilizer, biological nitrogen fixation, which is much, much more sustainable than the Haber-Bosch processes we're using now. I'm interested in recycling N for protein, things that would be well at home here in the Biodesign Institute. On the water side, you're already all about it, but it's water reuse. We're going to have to reuse the water, figure out how to do that. Aquifer recharge, because we've depleted them worldwide. Even in Iowa, we think we're water rich. No, we've depleted our aquifers, even in Iowa. We have to look at biological nitrogen fixation. If we can't do those other things, we'll have to try desalination. And on the energy side, I think you know the story there. Wind, solar, energy efficiency, batteries. My friends are running 39 models, which are being, all over the world, which are being used for these projections for the IPCC. There's a new report out, the Coupled Model Intercomparison Project 6, the sixth one of these 39 models, global models running all over the world simultaneously. And what they indicate is that the left-hand side is where we're going with global temperature. And we are heading towards the orange, which is sort of in the middle on the right-hand side by 2100. And that's about, I would say, 2.7 degrees Celsius warmer. Remember, we're at 1.1 degrees. So we're going to have to figure out how to adapt more than we have already because it's going to get hotter before it gets better. But eventually, if we make that adaptation and mitigate the emissions, it's going to get better. I'm here to tell you it's going to be better. I'm an optimist by nature. I don't know how you wake up every morning and keep going. Otherwise, I truly believe that we can do this and that it will be a better world that's created. The right-hand side, I forgot to mention, is the precipitation. I mentioned earlier that the hydrologic flywheel, we have hydrologists in the audience, is flying faster and faster. So places like eastern half of the United States are getting more rain, but it's coming in big events, flood events. Overall, the right-hand plot is supposed to tell you that the 39 models say we're going to have 3 to 5% more precipitation during this decade. During this century. I know this is too small, but I'll just say what it's about. I used the 39 models and looked up what Phoenix is supposed to be like, because I thought you might be interested. And basically, the middle 2 degrees Celsius warming, almost twice what we've had so far, would be visited by 2060 to 2080. And it indicates 10% less precipitation. That's the top one. And it indicates for Phoenix area. And it indicates that your soil moisture will get much worse, about 1 standard deviation less soil moisture than you have now. So what we have to think about in trying to keep up is how do we do any agriculture? You know, if we have 1 standard deviation less soil moisture. So our future is, I think we are going to experience warmer conditions. I think the IPCC goal of 1.5 degrees Celsius warming, that's 2.7 degrees Fahrenheit, we're going to pass that in about 20 years. So I don't think it's achievable any longer. We've already set up the system, and there's a long lag in the system. But I think we can adapt to that. We will have to adapt to that. We won't have any choice. And if we go about mitigating emissions, we can actually begin to turn that around, sort of like, hopefully, the blue line in this web of model realizations going out to 2100. More likely, right now, we're following the orange line with about 2.7 degrees Celsius warmer, 4.8 degrees Fahrenheit. That's a lot to adapt to. So we have to mitigate, number one, reduce our emissions. We haven't done that yet. We have to adapt because it's going to get worse before it gets better. Most of all, I would say we have to collaborate. We're doing a terrible job of treating each other with honor and respect and collaborating. I was at the Paris Agreement as a reporter. I got to cover and be in all the inner sanctum meetings, 197 countries in Paris in 2015. 120 heads of state came. They set the goals that we're now trying to reach. But we have to, it struck me at that meeting how people, for the most part, really did care about, especially the vulnerable countries. There's about 43 vulnerable countries. They've done the least. They've contributed the least to this problem in terms of greenhouse gas emissions, but they're affected the most. And somehow there's going to have to be collaboration, cooperation, yes, and even some transfer payments in order to make this right, in order to get them through this adaptation period that we're talking about. There's a lot of good news. I was asked about that today. One is the global methane hub. There's low-hanging fruit with methane as a greenhouse gas. I think we can control that, and I think we can stave off a good deal of warming as a result of that gas. The debt relief, we need to raise at least $100 billion per year for the kind of transfer payments that we're talking about for the most vulnerable countries. In the future, you know how we do environmental impact statements in the United States? We're going to have to do a climate change impact statement for every financial decision at the International Monetary Fund, the World Bank, and so on. Everything is going to have to look at this. It's that big. It's that important. In 4 days from now, that same group of 197 countries will convene in Sharm el-Sheikh, Egypt, to, let's hope and pray that they can seek a renewed solidarity between countries and go about this business. You know, regarding the energy, food, energy, water, we need to electrify most everything. You are doing that here. We need to use renewable wind, solar. Nuclear can't be ruled out, but it isn't going to help us much in the near future. We need electric vehicles. We need battery storage in all of those. We need a vehicle to grid such that the storage batteries, we have 240 million cars in this country. Just imagine if each one had a storage battery and they were hooked up to the grid such that they could put, we're talking about 60 gigawatts of energy. It's a huge amount of storage, such that they could put energy into the grid when you're parked at work or whatever, and take energy maybe at night when it's not needed from the grid. This creates millions of high-quality jobs, and it's how we go about rebuilding our infrastructure. You know, there was an economist, Joseph Schumpeter. I didn't actually like all of his economics, but he wrote about the creative destruction. He said the most sure way to generate economic prosperity and wealth is creative destruction, to wipe out the old and replace it with something new. And that's exactly what we're trying to do here. Wipe out the old, the fossil fuel age. I tell my students it's been a good run. For 200 years, we've used fossil fuels to do everything, but we're out of it now. And the replacement is what's going to be much, much better than ever before. It's a brighter future. We're talking really about improving the entire human condition. That's what it's about. I think that's what the Biodesign Institute is about, to tell you the truth. It's about sustainable development goals. Thank heavens there is a United Nations to talk about these things, at least, if not solve them, at least talk about them. It'll be a cleaner, I may not be here to see it, but it will be a cleaner, healthier, fairer, more resilient planet that we're creating. Sustainable development, better equity, diversity, equity, inclusion, because who suffers the most? The people who don't have anything, and they have to be included in this transition that we're making to a better world. We have to, in conclusion, we have to reduce global climate emissions. That's mitigation. We have to create a green climate fund for those vulnerable people in vulnerable countries, and the benefits are very many. Lots of good things are happening. I see it here in the Teslas charging up at your EV charging stations right here on campus. Lots of good things are happening already. They're just not happening fast enough. We got to catalyze that, we got to stimulate that, and we will eventually turn the corner on emissions and the carbon dioxide in the country. It's a great pleasure to be here. Thank you so much for the chance to speak to you.
We have time for questions, right?
I hope so,
Yeah.
a little bit.
Oh, we got a question back there.
Hi, thank you for a wonderful presentation. My name is Nivi Biani, and I recently graduated from the school Biodesign School in Civil Engineering a week ago, became doctor, and I've been an environmentalist.
Congratulations, Doc.
Thank you. I've been an environmentalist since I was 8. Brought my dad here to see your talk today. He came for my defense. In the meantime, it's been a week, and I've been interviewing with companies like Amazon and Google for the role of carbon manager. What would you tell me is the biggest, what advice would you give me if I were to get that role with them? And how could I make the most impact with companies like that when they're hiring in this role title? Thank you.
I talked with the students today. Thank you for that comment. And I talked with Brad Allenby today, too. And I asked Brad Allenby, you know, in your career, wonderful faculty member here at ASU, for those who don't know him. I asked him, well, in your career, what was the most important thing you did? How did you make a difference the most? Was it your time at AT&T? Or was it your books that you wrote with Tom Gradle and Allenby? Or was it your time here at Arizona State in teaching? And without missing a beat, he said right away, it was my time at AT&T. And he was involved in the Montreal Protocol, the most successful environmental agreement ever, which right now, if we hadn't had that agreement, the freon chemicals would be much bigger warming effect. They also destroy the stratospheric ozone, which shields us from ultraviolet radiation, but it would be much bigger than carbon dioxide if we hadn't done that. 197 countries agreed on that. Granted, it was only basically 2 industries involved, a very limited market compared to fossil fuels, but that was the most important thing. And then I said, well, what about Arizona State? And he said, oh yeah, that too. He said books don't matter very much. So what I'm trying to say is, your time with those kind of companies, you can really make a difference. I also told the students, we want all those companies to be prosperous. We want them to make money. We want them to create jobs. That's what we all should be rooting for. I want you to do the same. You're going to make a difference. Thank you.
Hi, I'm Deborah Hellitzer. I'm the Dean of the College of Health Solutions and here at ASU, and so you can tell that I'm very concerned about health. And I'm very interested in the question of electric cars versus hybrid. I'm going to look for cars soon. And as somebody who lives here in Phoenix and is very concerned about the amount of electricity that we consume for air conditioning and the problem with water and our inability probably to generate hydroelectricity, I'm wondering if you could talk about the advantages and disadvantages of hybrid versus electric cars.
Gosh, that's a great question, and I confess I am not an expert on that. You're really talking about a life cycle assessment, regarding the manufacturing and use, the mining, the materials, the manufacturing and use through the entire life cycle of hybrids versus electric vehicles. And I'm not sure I know the answer, but I really think that, for the long haul, if you're worried about that, a plug-in hybrid would be a good way to go, but that would be a third life cycle assessment. In general, we need to move towards electrification because fossil fuels, as I hope I've showed, are a non-starter in the future. So I would go electric.
Yeah, hi, I'm David Sklar, and one of the things you talked about was the increasing population, which clearly has an impact on our use of fossil fuels and everything. But you didn't say anything about maybe what we could or should do to try to limit that increase, because let's say we didn't go to 10 billion and just let's say we could even reduce the number of people. What kind of impact would that have on the overall problem?
I think in that, thinking about the whole human condition, that's really addressed in a way by the Sustainable Development Goals for 2030, and those have to do with each country having a plan, not necessarily transfer payments, but in collaboration with others to lift up especially women, for education. And we've made some progress in that, but the pandemic has made us slip back. When we have women who are educated and empowered, we have fewer children being born. And that might be maybe the only solution to try to drive down that 10 billion number that it looks like we're heading towards. But it's a great question. I don't pretend that population isn't a part of it, but I also would offer to you, in whatever it's worth category, the increase in population. When I was born, there were 2.5 billion people on Earth. Now there's 8 billion people on Earth. That increase is far less than our increase in greenhouse gas emissions during that same period of time. So per capita emissions and technology have contributed mightily to this problem that we're talking about tonight. Population does also, as you said, but it's not the primary cause. Yes.
Morton Monk in the School of Molecular Sciences. There are some early efforts to actually remove carbon dioxide from the atmosphere, in one case pumping carbon dioxide into basalt. Can these efforts really make a contribution to solving this problem?
To be honest, I don't really know, but I think we have to have the research to see if they could. My own answer would be nature, and the most natural way to remove carbon dioxide from the atmosphere is I would reforest immensely the entire world. All marginal lands, I would take then the forests when they reach climax, I would cut them and turn them into useful products, turn them into biochar, take the biochar, put it back onto the marginal land, replant the forest to keep it going. Because otherwise, that kind of decarbonation by nature won't work long enough for the problems that we have.
Thank you.
Hi, this is Rangarajan. I come from Europe. I live in Europe. One of the questions I have is, with all the simulations, we know how much we have to reduce by industry and as a whole globe. But can I get a number individually? What can I change? How much I should reduce? I'm a consumer. I drive cars. I eat. I consume energy. Now, if individual like me can reduce by 20 to 30%, can I save this planet? In the sense that I look at it, I'm not aware that I'm driving a car, I'm flying all the way and so on. I think it is time that I should get a saying, you cut down this today, tomorrow this much energy. Things like that would help individual citizens of the world to realize that each one of them have to do something about it.
I agree with you, and that's beautiful. And if as a professor, if I give you a report card, 20 to 30% sounds pretty good, especially since the recent projection says we're only going to decrease 1%. So yes, every one of us have to reduce our carbon footprint, and every one of us, we do make a difference. And thank you for that comment. I think you're absolutely right.
Hi, I'm Peter Williams. I'm also from the School of Molecular Science. I was actually hired by Mort Monk, which is one of the best things he did. But I have to say
that I am a pessimist in all this. If we even leveled out carbon dioxide, which I don't see much prospect of happening, we've still got enough to keep the global warming going on. So my question is, do you have any thoughts about the possible efficacy of various geoengineering schemes that have been proposed?
I'm sorry, circular engineer?
Geoengineering.
Again, as I mentioned earlier, we have to do the research, but I certainly hope we don't end up shooting sulfur shells up into the stratosphere. We know that works, by the way, but it doesn't solve the acidity problem of the ocean. There's two major problems. We could shield ourselves from radiation. We could decrease the temperature. I think it's entirely possible, but there's so many unintended consequences. I would say keep doing the geoengineering research in case we're like the painter who paints himself into a corner. But God forbid, I hope it. What I see us doing, I think we're going to sustain, but in a way, not everybody would maybe agree with that it's a sustain. I think we're going to kind of muddle through. It's going to get warmer, but good things are happening. We are going to make this transition, but it's going to take some time. And I hope that geoengineering, we already manage our agricultural land completely, as you know. We're managing the oceans to a large extent, if you count fisheries laws and so forth. And we're trying to manage the atmosphere, but really, are we going to do geoengineering to change our energy balance? I hope we do it by mitigation.
Thanks.
Instead. I'd be interested in what everyone else thinks, too.
Well, I guess I'm next. I really enjoyed your research. This is very impressive, but here's the issue that we have. There's 8 billion people.
8 billion?
And growing. Okay, so the research is overwhelming to the average person on the earth, okay? All we're looking for, each of us, is tell us when we wake up tomorrow morning, what is the one thing we should do to go fix the problem. That's what we're looking for, the one thing.
It relates to that gentleman's question also. I'd say that each person can reduce their own carbon footprint better in their own way. So I don't think there's one answer that we all could do. But certainly we all can do things to improve our own carbon footprint. I have tried to improve mine. One of them is less travel, but also electric vehicles, also planting trees all around my house to reduce have the temperature lower in the wintertime and higher in the summertime. And I think each of us have some low-hanging fruit that we can seize on and wake up that next morning, as you said, and try to help the problem.
Okay, thanks for that. And again, I was just looking for the one thing. I mean, you said plant the tree. Do I use less water tomorrow than I have? It's those little things that if we can all do it, we can make this happen. But I think a lot of people are overwhelmed. Great research. We know we're in deep doo-doo. I mean, we understand that, but it's the one thing, little thing that each of us, and I'm looking at, if you had the 8 billion people in this lecture hall today, I know it's impossible, but if you know what I mean, what could each of us do tomorrow morning
I'd say
just to
walk,
make a difference?
Walk to work or ride your bike, if you can do those things, that really actually adds up.
Thank you.
Yeah, I have a question.
Yes.
Do you think there are any fundamentally bad ideas that have traction right now that'll actually push us or pushing us the wrong direction? Because I can think of a few that seem like good ideas.
Anything to not keep it in the ground, the fossil fuels, oil depletion allowance, that's been around a long time. But discounting the resource that should never be used, that's just absolutely crazy. And that might be one that comes to mind right away that really is wrong-headed. even now with the war, between Russia and Ukraine, and the push, not just our president, but a lot of places to expand fossil fuels, I think we have to be very careful about that. We don't want to upset the entire economy. That's people's lives. That's poor people too. But at the same time, gosh, with the amount of progress we've made, we can't go backwards. We can't backslide. I don't know if that answers your question, but that's all I got.
Well, thank you all. Really good discussion, really great questions. Let's thank Dr. Schnoor one more time. That was a fantastic talk. Hope everybody has a nice evening, and we'll see you at the next one. Take care.